All right, this is a short mini lesson walking you through the beginnings of Unit 4, Worksheet 2. So, in order to do this worksheet, you really need to have a solid understanding of Avogadro's hypothesis. So this goes back to the gases and how they combine video you just watched yesterday. So in Unit 2, this is way back, we learned that the pressure that a gas exerts is directly proportional to temperature. In other words, if temperature increases, pressure increases. And we explained this with the number of collisions. If there are more collisions, there's going to be more pressure. So the faster particles move, the more frequently they're going to collide, which is going to increase the pressure in a container. So when we begin part 1, it's kind of a refresher question right off the bat. What was Avogadro's hypothesis about the number of particles in each container if the pressure and the temperature is exactly the same? So what we're really saying with pressure and temperature being the same is that the collisions, the frequency, the amount, the force of collisions is equal. And when the temperature is equal, we're also saying that the speed in which the particles move is also equal as well. So this must mean one thing and one thing only. If the particles are moving the exact same speed and they're colliding just as frequently as one another, this must mean that there are the same number of particles, or in other words, equal number of particles in each container. And this is what Avogadro's hypothesis states, is that gas containers that have equal pressure and equal temperature will also contain equal number of particles. So you've seen evidence that 2 volumes of hydrogen gas will react with 1 volume of oxygen gas to produce water. Think back to the electrolysis video that you watched in your elements versus compound stations. Every single time that hydrogen and oxygen were reacted together, 2 molecules of hydrogen always combined with 1 molecule of oxygen to make water. And this is where we derived the H2O formula. Now, we're going to represent this reaction with particle diagrams, and this was represented in the gases and how they combine video. You're going to want to have different colors out so that you can illustrate particles of different elements. So we're going to represent molecules of hydrogen, which I'll just draw here as a dot, with molecules of oxygen. Now, we've already talked about how molecules have more than 1 atom within them. But we're just going to go back to basics and just think of molecules as particles. Because at the time of Avogadro's hypothesis, scientists and chemists alike did not know that molecules contained more than 1 atom. So when they thought of a molecule, they thought of individuals the way I've drawn them here. So I'm going to draw my hydrogen molecules reacting with oxygen molecules to produce water. Now here are the rules with your particle diagrams. We're all going to assume that 1 box or 1 volume of molecules is going to be equal to 4 molecules, 4 particles. We know that all of these boxes are going to have an equal number of particles because they're all at the same pressure and temperature. So we're just going to all do it the same way and assume that 1 box is going to be equivalent to 4 molecules. So if I were to draw a box of hydrogen gas, it would have 4 molecules like so. So each of these boxes of hydrogen gas is going to have 4 molecules. And then 1 box of oxygen gas would also have 4 molecules. So when we watch the reaction between hydrogen and oxygen, it was always 2 hydrogen volumes reacting with 1 oxygen volume to make water. So my drawing of my water particles should come from the combination of hydrogen and oxygen. So I'm going to use a black pen to kind of help me keep straight what's happening here. So 1 of these hydrogen molecules and 1 of these hydrogen molecules is going to react with 1 of these oxygen molecules, and they're going to combine to form a compound, and that compound is water. So 1 molecule of hydrogen, another molecule of hydrogen is going to combine with another molecule of oxygen, and boom, that makes a water. Okay, so that makes sense. So I'm just going to keep going, and I'm going to react another molecule of hydrogen and another molecule of hydrogen with a molecule of oxygen. So let's see, one hydrogen, one oxygen. Perfect. Let's keep going. One hydrogen with another hydrogen with an oxygen is going to make another molecule of water. Perfect. And then I only have one more molecule left in each container. One molecule of hydrogen with another. And my last molecule of oxygen is going to make one more molecule of water. And this actually works perfectly because 4 molecules, we said, is just a box of particles. So I got the exact amount that I needed. Let me make that a better box. I got the exact amount of water that I needed to make one complete volume of water. Let's take that tool off. How do I take it off? I guess I just go back to this pen? Yeah. One volume. Okay, perfect. So how do the H, O, and 2 in the formula tell us about the composition of water? We've kind of discussed this already. The H means we've got hydrogen particles. The O means we've got oxygen particles. And the 2 just means that there are 2 hydrogens, whereas there's only 1 oxygen. And that's where we get our H2O from. So if you were to move on to the next page, the next question in part 1. In a like manner, represent the particle diagrams that account for the fact that 1 volume of hydrogen is going to combine with 1 volume of chlorine to produce hydrogen chlorine. What do you suppose the formula for hydrogen chlorine might be? So again, I'm going to do a legend. Remember, hydrogen is going to be purple, and chlorine, let's do a new color. Let's do green. Chlorine will be green. So you're going to illustrate the same thing that you did for water and find that maybe your molecules of hydrogen chlorine look a little bit different than your molecules of water. And hopefully this should help you deduce what the formula might be for hydrogen chlorine. And then you're going to do number 4, and again, you're going to see that maybe your formula for ammonia might be different than the formula you got for hydrogen chlorine and water. Now, that being said, I think you're well equipped to do numbers 3 and 4. Part 2, you might need a little bit of assistance getting started. Part 2, you're doing the same thing you did in part 1, except we're considering one key thing. Chemists occasionally found that 1 volume of gas A would react with 1 volume of gas B and make 2 volumes of product. And that was kind of confusing because 1 and 1 typically made 1 volume, like you'll see with hydrogen chlorine, typically. Just like we saw with water, only 1 volume was typically produced. So when 2 volumes was produced, it led chemists to be a little confused. And what they discovered is what we have already known, is that molecules contain more than 1 atom and oftentimes contain 2 atoms. So in part 2, what you're illustrating is hydrogen. Instead of as molecules made of 1 atom, you're illustrating hydrogens as molecules of 2 atoms. And instead of illustrating chlorines as molecules of 1 atom, you're illustrating chlorines as molecules of 2 atoms. And seeing if this can produce 2 volumes of hydrogen chloride. That being said, I think you've got enough of the foundation to begin work on part 1 and begin work on part 2. You're going to have questions as you're going through this, and that is exactly how it's designed. The questions is going to be where the real learning happens. So please take every opportunity to ask as many questions as you can.